Welcome back to episode 2. Actually, thank you for coming back for episode 2 of this. I thought I scared you off in the first one already, but
I
turns
know.
out I was wrong.
Why
Or you just love the struggle so much. This week, I got a different question for you. I had my chem tutoring session and I had this question, and I realized it had nothing to do with chemistry. It was a full maths question, and the kid really struggled with it. And the question was around converting units, and it's something that I find all my chem students struggle with. But it's also that one question or two questions that VCAL will put in an exam to separate kids. Which is kind of weird because it's very much more of a numeracy activity than it is a chemistry understanding activity. But yeah, they'll add it into questions, and students because it's a little bit more implicit in the study design. It doesn't say you have to be able to convert units. You obviously do, right? If you're dealing with different calculations. So I really struggled with it, and I realized conceptually that I don't think students understand conversion between different units.
Yeah.
So I sent you the question, if you don't mind bringing it up. Okay, sweet. This is a question I have kept the students working out. So this was a SAC question actually for the student. Sent it to me. We went through it.
Was this from an exam or was it a SAC question? So it wasn't a VCAR question?
It was from a SAC, however, could easily have been a VCAR question. Does that make sense?
Yeah.
Yeah. So the skill could easily be transferred into an exam. The word for word question, not an exam question.
Yeah.
So, if you read through this, blah, 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 the question is asking you to calculate mass of kerosene, but it's got nothing to do with chemistry. So the kid could have just gone straight into math mode and figured it out. However, you can see that there was they were very lost in here. And to me, that represented the fact that they don't actually understand what units represent, and therefore how to go from, say, grams to kilograms or liters to milliliters and how that works. So can you help me, if you were a maths teacher, how would you have deconstructed it conceptually as something to understand conceptually rather than as a formula or as a chemistry or something?
So when I first looked at this question, I also thought it was just predominantly a maths question. But then when I started unpacking it, I realized that unless you understood what the chem component of it was, particularly the density part, you also were going to struggle to understand it. The conversions weighed in really heavily, and just from a maths perspective, I was looking at it and unpacking it in a way that I thought initially it would work in a maths class. But then when I got to the density part, that's when things predominantly took a chem turn. So if I was to, because conversions, we look at converting year 7, year 8 in maths. So we could do that quite easily. Like I look at the typical plane uses 4 liters of kerosene every second, calculate the mass of kerosene in kilograms used over a 60-minute flight, given that the density of kerosene, it looks like there's a lot of math, and there is a lot of maths, but unless you understand the chemistry, I think students in a maths class at that year level, year 7, year 8, when conversions come in, will kind of struggle. So this is one of those really unique questions, or maybe not unique, but really important questions where chem and maths completely overlap. Do you know what I'm saying? So
can I ask you a question before you go on?
Yes.
From a maths teacher's perspective, how do you explain to students the concept of a unit? Like, for example, like centimeters, millimeters, but here, the unit here for density is grams per mil, right?
Yeah.
So that's just a unit. So different units have different sub. Do you know what I'm trying to say? Like, how do you explain to a student what a unit like grams per mil actually represents?
It's a really interesting one because we don't often explain it in any way other than we're using the words per, and the word per in maths means division or out of something, out of, like the word per cent, out of 100. But when we're looking at those units in terms of those proportional units, 0.8 grams per milliliter, that -1 up there to the -1, that means a division. But that's kind of forgotten. along the way, those tiny incidental little maths things. So if I was to look at this, if we go 0.8 grams ml minus 1, that actually means there are 0.8 grams for every 1 milliliter of kerosene.
Okay. So if you break it down like this, I would argue that there's no chem in this.
It's a predominantly maths question, but unless you understand the chem nuances, like what is density? So density is a chemistry concept, but when you give it to students like a chemistry concept, they still need to understand it really deeply from a maths perspective as well. So it is a maths problem, but it contains some chemistry components that the students need to understand, and that is predominantly the density component.
Right.
And honestly, I agree with you to a certain point, because there is a lot of maths involved. This is a 3-mark question. It's not like the one that we did last week, which was worth 1 mark, and you had to use your gradient and understanding of graph for 1 mark. This is 3 marks, and I would argue that 1 of those marks is chemistry and 2 of those marks is maths related. So yeah, you're right. It is predominantly a maths question.
Okay, so there's multiple conversions that we mentioned here, right? We've got mass conversions, we've got volume conversions, the mils to liters, then we've got time as well, every second. So how do we go about doing something like this?
Okay.
How do I teach it conceptually?
Do you want to know how? This is how I did it, because whenever I come across a question like this, I always need to fall back on my conceptual understanding of maths, what's actually going on. So I always need to draw myself a picture just to be able to compartmentalize every aspect of what's going on here. So this is how I did it. The first thing I looked at was a typical plane uses 4 liters of kerosene every second. So when I use comparisons, I like to use bar models. What I did first is I made a comparison of 4 liters for every second. So I drew it out like this. I went, condition 1 was like this, 4 liters, 1 second. Then that was like condition 1.
Okay,
now, because
I'm going to interrupt a lot for this one.
Yep.
Purely because I have a suspecting feeling that a lot of teachers don't understand the bar model.
Yeah.
Or teach from a bar model.
Which is really unfortunate. This is why students don't get it, because, when you're doing this kind of model with the conversion, like 10 millimeters, 10, 1 centimeter, like
which is how we teach it.
Yeah, it doesn't, it's conceptually, that doesn't make sense, and students will forget it. So they need to make that comparison of proportions, and these bar models, they need to be used more in the classroom. So it's going to be very bar model heavy.
Okay, so I'm going to ask a lot of questions about this.
That's
even for my own understanding too.
Please do, because I know a lot of teachers, you're right, a lot of maths teachers and a lot of teachers don't use the bar model here in Australia. They're used a lot overseas, like Singapore uses it heavily, parts of the conceptual curriculum in the US use it. It's only starting to make an introduction into the maths.
Because the jumpy thing, like I reflect now in the maths classroom, that jumpy thing is a visual representation of a strategy, right? It's not a concept, it's not a visual representation of a concept. So
it's a model to represent something that is not conceptual. Yeah, it's a process. It's a model to represent.
It's a process. Yeah, it's a strategy. You just multiply by 10, you divide by 10 or whatever. And so really that is probably not the best way to use models like that. You know what I mean? Like I think about it now, I was like, oh, damn. So there's a few things that I've noticed here in your bar model that I want to question.
Yeah, so go, question.
The first thing is I noticed that both of them are the same length.
They have to be the same length.
So why? Why is that?
Because what we're doing is we're saying that one is proportional to the other. So when you're comparing, so it's kind of like if I was to compare 10 millimeters, so 10, let's say that's 10 millimeters to 1
centimeter. Got it.
Centimeter. All right. So basically what we're saying is one will fit into the other.
Okay.
If we were to build it, they would be the same size.
So you can imagine a ruler, right? I'm imagining a ruler right now.
Yep.
And the big sort of lines for the centimeters, the small lines for the millimeters, and they fit snug in one, like 10 millimeters. Okay,
Exactly.
got it.
It's kind of like one very simplistic way that you could draw it is something like this. So you could say, if I said 2 and 3, that would be equal to 5.
Got it.
So we're looking at equivalence over
Okay.
here. Okay, so we're
Mhm.
looking at equivalence. One has to be equal to another. So you can imagine that there's an invisible equal sign between here.
Sure.
So what we're saying is, we're not saying 4 liters is equal to 1 second in this case, but we're saying that for every 1 second, we have 4 liters of kerosene being used.
Sure. Okay.
Yeah. So that's
right.
the kind of thinking that I went for
Okay.
here.
Okay.
And I need to do these things because it's just how my brain works. I need to be able to unpack things visually. I recently actually read an article where they did a study on people's problem solving, your students' problem solving, like 13-year-old problem solving skills. And they found that students who actually drew a representation along with a real life kind of thing. So even if they were given an image, if they drew a representation, they actually performed better than those who didn't.
Okay.
So drawing is important. That's what I'm talking about. Okay, back to it.
So I know that 4 liters, I mean, we're talking about equivalence and proportion. So for every 1 second, I'm imagining that 4 liters accompanies that 1 second.
Yep.
Right?
Yep.
Okay, cool.
Yep. So 4 liters of burned every second. So that was
Yep.
the first condition. The second condition I noticed was that we wanted to calculate the mass of kerosene in kilograms
Mhm.
that's used over a 60-minute flight. So the flight was for 1 hour. So
Mhm.
then I drew another condition, and this is where the conversions come in, because here we're talking about seconds, but here they're talking about minutes. So I drew myself another bar model that showed how many seconds in 1 hour, 60 minutes.
Mhm.
It was 1 hour.
Mhm.
My writing is horrendous. This is what happens when you're a left-hander. You just can't write. Anyway, so we've got now condition 2. So I'm going to call this condition 2 because we know that there are 3,600 seconds in that flight. So if we know that there are 3,600 seconds in that flight, and for every one of those seconds, 4 liters is burned. So what I'm now going to do is I now know that I'll multiply my 4 liters by 3,600 seconds. So that will be the total amount of kerosene used in the 60-minute flight.
If I'm a student
Mm,
and I'm seeing these bar models,
mm.
to me, the size of the 1 second and the size of the 3,600 seconds is the same.
This is why when you're doing these bar models, you have to introduce them at a really early stage,
Got it.
because it's really difficult to do them proportionally. So the bar models are supposed to be a representation of something. So kind of like, when you do a triangle and you're saying this is a right triangle, this is 30 degrees. Now, it doesn't necessarily mean it is 30 degrees, but it represents the mathematical situation. You know what I mean? And when you're doing anything, just like what we talked about last week in the graph one, we talked about taking it all the way back, unfortunately, taking it all the way back and building that initial conceptual understanding of what's actually happening in the graph so that we can then use that understanding, transfer it into the problem that we're doing. So that's a whole lot of work for you as a chem teacher at year 12. And again, this is why we're doing this, because we want to be able to go back and go, all right, well, what do we need the teachers at the year 7, year 8, year 9 level to be able to do in order for the students to be able to transfer their skills better at year 11 and year 12 in VCS science?
Because what would have been an ideal situation here is that you have that 1 second bar and kids will be literal.
Yep.
And they go, Miss, but you've got 3,600 seconds there. So what we should have, I mean, in an ideal world, we draw a bar that's equivalent to 3,600 lengths of that 1 second, right? So
Yeah.
conceptually, they would actually understand that there's a lot of these 1 seconds in that
Mhm.
3,600. And then you
If
ask, well, how many lots of them are there? And that's how they get to the times
Exactly.
3,600
If
part,
I
right?
didn't have if I was to really do this, but,
Yeah.
I don't have a lot of room on my screen, so I
Yeah,
didn't.
yeah, I
So
understand.
this is what I'm gonna do, right? So I'm gonna try to do it in a way. I'm gonna rub this out. I'm gonna try to do it again. But
No.
ideally, I
No.
know all that work, it was so pretty to start with. So ideally, I'd have something like 4 liters, 1 second, and then
Right.
under here,
Yeah.
I'd have this really
3,600.
long bar that
Yeah.
says 3,600
Yep.
seconds, and then underneath that, I'd
Yep.
have 4 times 3,600 seconds, and that would give me the how many
Yep.
liters. You
Yep.
know what I mean?
Because when students do it mathematically, right? And
Mm.
I see this all the time with my kids. It doesn't matter what level skill they do.
Mm.
They go, I know I've got to do something with the 3,600. I'm going to take a bet. I'm going to roll the dice. I'm going to say divide by, and that's it. And then move on. And then
Yep.
when you go back and you go, hang on, but why did you divide? And they would say, well, I wasn't sure. I wasn't actually sure what to do, but I knew I had to do something with the 3,600, which suggests to me that conceptually they don't understand, like that the question is saying you've got groups of the 1 second enough to fit into 3,600 seconds. And
Exactly.
so you say, well, it's time to divide. I had a 50-50 shot. I'm just going to pick one. And then
A
get to
and
the end and go, huh? Why is this number so small? You know what I mean? Like it's that.
Exactly. You've actually hit the nail on the head. And if a student can even reason to point where they say, this is a really small number, can't be right, like you would hope that they would at least
Yeah.
be able to do that. Sometimes they can't even do that
Yeah.
because for them, maths is so abstract
Mm.
that whatever number they get doesn't make sense to them anyway, whatever answer
Sure.
they do you know what I mean?
Mhm.
So you know, I have this, I'll tell you, a tutor, a beautiful young girl, year 10, and we were doing some trigonometry, and she was sort of getting the hang of all of the trig stuff, and then purposely gave her a question that required her to convert units. And she knew, like, initially she was like, well, I know that this is in centimeters and I know that this is
Mhm.
in meters,
Mhm.
but she ended up saying to me, I can't remember what
To
the arrows, I
multiply
know
or
the
divide.
arrows go this way
Yeah.
and I know the arrows go that way, but
Yeah.
I don't know how much is in what. And
Yeah.
so teaching that table, that
Mhm.
heuristic where they just like,
Mm.
it's honestly, teachers, it is useless for you to do that
Mm.
unless you give them little model to
Mm.
have it in front of them and use at all times. But
Mhm.
even then, they do not understand what is happening. They just know I'm supposed to use it and follow the direction of the arrows and what it tells me to multiply and divide by.
Mhm.
So this to me is a better way. At
Interesting.
least this way they can kind of visualize conceptually how far something is. I ended up having to say to her, so from here to our local store is 1 kilometer.
Mhm.
How many of these centimeters? So I had to take out a meter ruler and I had to actually create a physical bar model. And
Mm.
so then she would realize that, okay, I've actually got a lot of little centimeters that fit into that kilometer. You know, she was then able to visualize it
Mhm.
from a distance perspective.
Mhm.
And that kind of started to help.
Interesting.
But unless you do that,
Yeah.
and for me, I think the bar model is the closest you can get to that representation.
So what I'm receiving from what you were saying is two things.
Mm.
By teaching that heuristic, which we thought was the right idea because it's in books, it's how we were taught.
Yep.
We've increased the cognitive load because they've had to learn a fact,
Mhm.
right? And a fact that's more of a strategy than something that's true about mathematics, if that makes sense.
Mhm.
And then secondly, if that's how we're going to get kids to remember how to convert, and kids are screwed from both of the examples that we've given if they don't remember what to do in which way, if that makes sense. Like if you go from centimeters to meters
Mhm.
and you don't realize that you have to divide because the number gets smaller, then you have no way of anchoring that heuristic. Because then
Mm.
you go, well, then going the reverse is the opposite. So if you get it wrong the first time, well, whatever your anchor is, then you have no idea of which way to go, except for the fact numbers like 100.
100%.
Right.
Because your immediate reaction to going from centimeters to meters is, if I'm converting 2 meters to centimeters, my initial reaction would be to divide because centimeters are smaller.
Correct.
You know what I mean?
It's, it's like word for word what my kids say. Oh, meters is a bigger unit, so it must be a bigger number.
So it must be a bigger number. So this is what they do because they don't conceptually understand. But if you think about it conceptually and visualize it, like here is my meter ruler and here is 1 centimeter. So let's say this is 1 meter, 2 meters would be like bigger.
Yep, keep going. Yep.
Keep going.
Yep.
So I've got 100 of these centimeters in there. So therefore I must have 200 of these centimeters all the way across.
Interesting.
So
okay.
just getting that rather than go, do I multiply? Do I divide? Think of it conceptually, like they will automatically know whether to multiply or divide because they know it's getting bigger. Like I'm getting more of those small things in a larger thing.
Okay.
You know what I mean?
Okay. Sweet. So if we go back to the example and the question, let's just say, ideal world, I have enough space to have a bar that's the equivalent of 3,600 of the 1 second units. Okay. So that means that to get to the hour, I need to multiply the 4 liters by 3,600 seconds to get to the total. Right. So that's the first step. The first step is, and the thing with this is like with these conversions, they can go any which way they want. It doesn't really matter. You don't have to go in this order, but you just have to understand how to go from one unit to another unit.
Yeah.
Okay. So the first thing we've established, and so the part A, which is probably the first mark from the 3 marks, is to go from this to now however many liters that we've got, which calculates to be what?
I think it's 14,400.
Yeah. So we're saying we've got 14,400 liters.
Yes. So
that second bar then underneath is what, 3,600, right? Is that right?
All right, we'll be 100 again. So we've now got, and these are supposed to be the same size, guys. So don't come at me. I know they're supposed to be the same size. So we've got 14,400 liters.
Okay, great. So we know that there's that many liters. Okay, great. So that's the first step. Now I know that that's in that 60-minute flight. I'm going to use 14,400 liters of fuel.
Yes.
Okay. The last part is to go from this bit and going, well, hang on, how many kilos is that equivalent to then? Is the last question.
That's the hard part because this is where the chem comes in. So this first part, this is predominantly maths. I just have to know how to do my conversions and what it all means. But this is the density part. And so this is what I did. I would draw another bar model. So I know that there is 0.8 grams per milliliter. For the students to understand what that means, I think the best way that I've explained this in the past is to say that water has got, and correct me if I'm wrong, the same mass as it has, mass to volume ratio is the same, correct?
Sure, let's go with that. So you're saying the density is the same, 1 mil to 1 gram?
Yeah, 1 mil to 1 gram. But not everything has that same component. So it's where density comes. So for every 1 milliliter of kerosene, if I was to weigh that, it would weigh 0.8 grams. So you can see here, it's the per 0.8 grams per milliliter, and I'm using the bar model as well as a comparison.
Now, see, to me, from what you've explained, it's no different to saying 4 liters per second.
4 liters per second, exactly.
Right? Like it's 2 units, and together you make it,
But we have an issue here because we have 14,400 liters. So we want to know how many milliliters that is. So we can do a couple of things. I don't want to do the conversion of milliliters to liters. I'd rather, from a conceptual perspective, what I worked out was how many milliliters would be 14,400 liters.
Is that not the same thing?
It is, but then we don't get a decimal.
Okay, got it.
You know,
so you got a whole big number.
So we got a whole big number. So if I go, let me think. For every 1 liter,
Bro, you got to make it big for my dumb brain. Like,
okay.
because that 1 liter looks smaller than 1 mil.
Yeah. I'm gonna,
See, this is like what kids literally think.
Yeah.
Right?
So let's say 1 liter is 1,000 milliliters. So 1 milliliter is, let's imagine that there are 1,000 of these in this,
Mhm.
and for every 1 liter,
Mhm.
there's 1,000 of those. So that's the conversion. So you can see now there's a lot happening here, because we're imagining that we're introducing conversions, we're introducing, how many milliliters in liters, mass and volume and grams and seconds time. There's a lot going on here. So I then know that in 400, I've got to multiply that by 1,000.
Sure.
Yeah. And that will be how many milliliters?
Mhm.
This is a lot. Now,
Yep.
I wouldn't expect a student to perhaps solve it this way, because I would hope that the student would know, coming across a question like this at year 12, would understand their conversions a little bit better. But, okay, so you're shaking your head, so obviously no.
No. You hope so, but you don't.
Yeah.
They don't.
But the idea is that if a student understands these bar models, they can work through it in their mind, right? Step by step. They can kind of
Mhm.
work through it, problem solve their way through it. So it's going to be 14,400,000 milliliters.
Mhm.
Now, for every one of those milliliters, it weighs 0.8 grams.
Mhm.
All right.
Mhm.
So that means that for 1 mil, I have
Mhm.
0.8 grams. Here's my tiny 0.8 grams.
Mhm.
I would then multiply that by 14,400,000,
Mhm.
and that would give me my total weight, 11,520,000 grams.
Mhm.
Grams,
Mhm.
which is 11,520 kilograms.
So again, going from grams to kilograms, you could have done the same thing, the bar model.
I could have done the same thing.
All of those, each step of those conversions is 1 mark. So you can see that you did 3 lots of conversions.
Mm-hmm.
Had nothing to do with chem. If a student actually conceptually understands as a mathematician what it means to have grams per mil, so if they had it as a fraction and they created an equivalence fraction, like equivalence on the other side as a fraction again, could have solved it.
Yeah.
Didn't need any chem. This is what I
Yeah.
mean. Like if students actually understand what units mean, like life would be really easy, because it's a representation of an equivalence, what you're saying, right? And you're saying that relationship doesn't change no matter how much you extrapolate it. Like it's always going to be 0.8 over 1. It's always going to, like what do you call it? The gradient is going to be the same as linear. True?
Yeah.
So no matter how big or small you make it, that gradient never changes. So you can
Yeah,
make a fraction equal to another fraction, because you're
Mhm.
saying the equivalent, like the relationship before and the relationship after will change, even though the numbers are different.
Yeah.
So the way that I taught it was, so conceptually, I think I'm still trying to figure out how to incorporate things like the bar model, especially at a year 12 level when they've never seen it before.
Have you used the bar model before?
I have, and the kids are like, what?
Yeah.
Because they've never been exposed to it before.
What I've explained here, from your point of view, conceptually, doesn't make sense, or is it still like, huh? Okay.
If everything was to size and proportion,
Yeah.
it's easy. You go, see how that's so small? See how many of those fit into this big line? Amazing.
Giving the kids the tools, teaching them how to use the tools, and then giving them a problem where they don't know what the method is to get to, that's the whole idea of problem solving, right? Is that finding the solution to a problem where you don't know the method. But if you've got the tools to tackle it, then you can use those tools to somehow problem solve your way through it. And
That's what I'm trying to get at. I'm trying to run away from strategy, from heuristics, and then go, in an ideal world, you'd be able to problem solve this based on conceptually what you understand about conversions,
yeah.
right? And then they can kind of logic their way through it, as opposed to, which formula do I have to use again? You know, like, that's what I mean.
Honestly, it's the biggest, along with differentiation and assessment, problem solving is one of the biggest questions that I get from schools. Can you come and help us, particularly secondary level, come and help us with problem solving? Because by the time the students get to VCE, they've realized these kids do not know how to sit with a problem, don't have the tools to unpack a problem. They really just don't have the strategies that they need to be able to transfer any of the skills that they've learned at those junior and middle school levels to problem solving. It's a big problem. It's not just in chemistry, it's in maths, it's in all other sciences as well.
So I will out myself here, because knowing this and having these conversations with you, when I step back into, the scenario where I'm teaching, and you're faced with the fact that you've got the year to teach the content, I don't have a year to teach the math skills associated with it. So,
yeah,
right? And so I cheat. I give them a strategy, right? And I go, I cheat. If you do it this way, it will work every time. And if I dictate it, I'll get you to write it on the screen, right? So this relationship that I've got here, 0.8 grams.
Okay.
Over 1 mil, which is what you said before. You said out of or of, it's a fraction, right? So that fraction represents a relationship.
So the language of fractions is really important, and the over, it's one of those notations that I recommend that teachers don't use, because it is 0.8 grams out of 1 mil, because over just means that two separate numbers, that they kind of don't conceptualize it as a fraction, as a part out of a whole.
So I've got that. And so pay careful attention to the units, right? And I go, okay, that's a relationship. The relationship never changes. You write an equal sign.
Yep.
And so we know that it's mass over volume, right? Mass over volume, right? Because that's how we've represented this relationship. Yeah. So instead of, right. But so I don't say it's mass over volume. I say, okay, well, if that's the case, and I'm trying to find the mass of the other thing, then the numerator in this case, in the next fraction, is whatever we're trying to find. So X, right?
Yeah.
And
so you're trying X over
the 14,400,000 mils.
Yeah.
Mils, right? So, and I say, as long as you keep the units in the same spot, so if you're going to keep mass as a numerator, keep it as a numerator once you create the new fraction. Same, vice versa. So you flip it around, it doesn't matter, right? But so let's pretend that middle part, the m over v, doesn't exist. And then one of the equal signs, whichever one you want. Yeah, okay. So now we've got a fraction where kids are like, oh, I know how to solve this. I know how to solve for X. And you go, okay, cool. Well, in this instance, you find X however you want to. You can cross multiply if you want to, or you can actually do each of the steps if you want to. But if you set it up this way and you're saying the relationships are the same no matter what the numbers are, you will never go wrong.
Yep.
And that's
that's it. It's exactly. But how good is this though? Take a look. This is exactly what I have done.
Totally. It is. You're right. But I've skipped the whole reason why that fraction or that working out is true, right? I've skipped the whole conceptual part of saying, you're saying that out of one whole, 14,400,000 mils, how many do you have altogether? When out of 1 mil, you've got this much. So the relationship is the same. This is a numerical way to represent that relationship, where your Bartle model is more of a model, like a visual way to represent that relationship, right? But I feel like if I had infinite amount of time and I taught the kids the bar model first, and then we came into year 12, they would be able to set up this relationship by themselves.
But also, if you used both, because the CRA model, the concrete representational abstract model, is based exactly on this thing. So it's got a lot of research behind it, evidence behind it that suggests that it is a really great way of teaching an abstract method. So let's forget about the concrete part of things right now, and let's just focus on the representational and the abstract. So if you can get the students to create this representation first in one example and say, this is why this works, then from now on, you need to use that method. Like, we don't want kids to be using this method. And that's the whole idea of the CRA model. The whole point of it is that we want the students to get to the abstract, because we don't need to be drawing models and images and pictures, but we can go backwards and forwards if we need to. If we're comfortable with this and if we've got it, that's where we want to end up. But for those students who don't remember the formulas, who don't really understand how to use or how to do this, then they can fall back on their conceptual understanding and draw the representations.
And this is why I was like, you know, I would argue that this is a math problem than a chem problem.
Look,
because if you understand units like this, then, you know, you didn't need the chem. Like, the only chem thing in there was the word kerosene, you know, like, if that. So this is, I think,
density.
Well, and that's why I was, that's why I'm like, is there a way to get the kids to understand units and unit conversions and how to do that, and then get to this? Because I had to skip the whole thing. I had to skip it and go, just create the relationship, keep it the same, and you'll never fail if you know how to rearrange formulas. And then you've got kids who don't know how to rearrange formulas, and you go, okay, fine, just cross multiply. Fine. You know, and then you get to that space and you're like, oh, let's not even go there.
I feel you. I know we can quite easily talk about everything that we've done here, but when you're putting it into practice, I know, you know, we all know that time constraints, by the end of it, you're just like, just use this, okay? Because I don't have the time to teach you everything that, you know, we've all been there. So if there is an opportunity, though, if a large portion in your classroom of students don't understand, then, you know, let's come back to something like this and say, okay, I now have, because for teachers, especially science teachers, they get to a point where they're like, I don't know how to teach it to them so that they will understand it. Okay. Because this is stuff that they should have learned perhaps 4 years ago, but they haven't got the understanding. And I don't know how to do it. So if you do get to that point, these models over here, these just provide you with some tools to put in your toolbox for the times where you really need to get them to understand. And if you have that time, then just pull them out so that when they do say, I don't understand why we're doing this, you can say, this is why.
Awesome. Well, look, thanks so much for your time. I think this is, like last time, it was a very rich discussion. And I think there are other points for future conversation as well around how we deal with like equivalence, how we then deal with proportion, because we both know that proportionality is a huge deal with junior math in particular, and how students don't understand that. So cool, but save for another day, and I'm sure I will send you some more questions for us to mull on and argue about. But until then, thank you so much for your time, and thank you to the 1 to 2 listeners who have seen this or listened to this. Appreciate it. Please reach out to us if there's anything that you want to discuss or if there's anything that we can do to help. Otherwise, thank you for your time, and we'll catch you in the next episode, whatever that may be. Thanks, Nadia. If you have any final parting words for everyone.
My parting words of wisdom. Sometimes it's okay to use a teachable moment to go off on a tangent and teach something or go over something, spend a lesson on something that the students are hooked into. If you find a hook in your classroom, in your teaching, take that teaching moment and use it. Don't be bound and restricted by the time of, you're not going to get through that by a certain time. Just use your moments. It's those incidentals that make the best teaching moments. That's my parting words of wisdom.
And there you have it. Parting words of wisdom from Mathsplaining Science. Thank you, everyone. Catch you next time. Bye.
Catch you soon. Bye.